Hello ladies and gentlemen, welcome to the May 2018 chemistry paper, real GCSE exam, an hour and 45 minutes, well done for sitting through that. So anyway, question one, give you the sort of substance that can react with an acid, and it just say other substance because it already mentions metal oxides. So for those people that wrote metal oxides or gave an example of a metal oxide, that's why that one's marked wrong. A base is also a metal oxide, so you can't say base. Words you can say, nice and easily, alkalis that react with acids, quite an easy go-to. And anything else that we put down when we're doing our acids and alkalis topic, acids and metals topic, we said that there's 4 equations. We looked at carbonates making carbon dioxide in the funny way that I say it. We also talked about hydroxides a lot because they are alkalis. We also talked about metals, and then they gave off their hydrogen and squeaky pop. So hopefully you can envisage where we saw that at some point. For 1.2, keyword here, and it's a keyword that comes up a few points, is the formula. A formula is where we've got the symbols and how many there are of each atom. So do make sure you know that one because it has cost a lot of people marks on this. The other thing that cost people marks is that you saw that the calcium's got a 2+ and the nitrate's got a minus, and you need to have 2 of the nitrates, and it's how to represent that, so it does require brackets. So we've got the Ca ones, look at the mark scheme, and then we've got the nitrate with brackets around it, and a little 2 next to it. Please make sure that you put capital C, a lowercase a, and then capitals N's and O's with the numbers smaller, subscript below the lines. Okay. Next one, straight in with a 6-mark question. I'm sure you loved seeing that when you sat in this for me. But it's one that you will know because it's dead similar. It's almost the same as when you did the blue crystals for me, which you did. It's a 6-mark question, as a practical, as a required practical. So this one should be coming out of your nose by now. Chemistry. Anyway, so what you need to be saying first of all is, oh no, it's not copper sulfate. Those people that started writing that you're adding copper oxide and sulfuric acid, naughty. Those people that just said add your acid, your dilute acid to your metal oxide, you've lost out straight away here. What we're making is magnesium sulfate. So to make magnesium sulfate you need magnesium oxide, and then to make the sulfate you need sulfuric acid, not just a dilute acid. Okay, so some people weren't in the top level of the questions because you didn't tell me how you'd specifically make magnesium sulfate. So once you started mixing them together, you're going to need to keep adding the magnesium oxide in excess, is the great way of saying it, because that means that you're going to keep adding it until there's no more reaction from the sulfuric acid. At this point, you know all the acid has been used up and is now gone. So you're left with a mixture of this magnesium oxide solid floating around in a solution which has got your water and your salt that you want to extract. So the next step, probably the next paragraph or next set of bullet points, you're going to talk about how you can separate out the next thing after getting rid of the acid. So the next thing we're going to get rid of is the magnesium oxide, because we're going to filter that out. It's insoluble, so then the liquid will flow through the solution, and then in the bottom, in the filtrate, the conical flask, you'll have your water and you'll have your magnesium sulfate. So then you need to, again, your paragraph, separate it out, explain how you're going to separate out your sulfate from your water, which is, it's evaporation, it's crystallization. So heat it up in your evaporating basin. You don't need to evaporate it to dryness, you can actually just leave it for the crystals to form. Some people even put stuff like hair dryers. Yeah, that's not exactly scientific, but it works in a pinch if that's what you can remember, because we're looking at heating up the water until the crystals are left to form. Question 2 then. The formula, again, is another time we see the word where it's scuppered some people. So if you look at the picture, for every black one there are 2 grey ones. Even if you counted up all 9 black ones, there'd be 18 grey ones, and the ratio for that then is for every Fe there is S twice, so that is FeS2, again with the capitals, the lower cases and the small number. It's not asking for an equation, so don't write an equation, it's not a reaction. For question 2.2, generally well answered overall. You've got Fe 26 at the bottom, 56 at the top. The 26 at the bottom is the atomic number. That tells you how many protons there are. So you'd have 26 positive protons as our first gap. And because we know we've got 26 positives, we'll also know we've got 26 negative electrons at the bottom. To find the number of neutrons, we're going to look at the numbers that are here. We've got 26 protons. We've got a total mass of 56. So out of those 56, 26 of them are protons. How many are left over? There'd be a difference of 30. That means there's 30 neutrons. Moving on to question 2.3. It says here, differences between iron and sodium, and it's making it clear one is a transition metal, one is in group 1, and we want to know about the properties. So the first thing that people were getting wrong here, we weren't talking about properties. So if you were talking about electrons, orbitals, energy levels and things like that, that's where you went wrong. Properties are things that are features of the material overall. So we're talking about things like melting points, boiling points, density, strength, coloured compounds, catalysts and things like that, malleable, ductile, sonorous. Now, some of those apply to all metals and some of them apply just to specific groups. So you can't say iron conducts electricity because so does sodium. We're looking for something that is different, so we need to get some comparatives in there. So we need to say things like iron has a higher melting point, or is denser, or is harder, or iron can be used as a catalyst whereas sodium cannot. Okay. The other thing that I noticed on that one is some people put more than 1 point on each sentence. So you give me more than 2. It's just say just give me 2. So let's say you gave me 8 things and 3 of them are wrong. The 3 that you had wrong just cancelled out all the other ones that you knew. Okay, so you need to just pick the best 2 that you know and put those down so you don't lose any marks for writing wrong answers. Okay, you're not going to lose marks if you just guess wrong answers. You can just score 0. But if you write down correct ideas and then write down wrong ideas next to them, you're going to score 0 still. Question 2.4 then. Again, this one's quite well done actually. People quickly spotted that this was a displacement reaction, or as some of our crew likes to call them, Kincaid, or let's throw some Channing Tatum in there just for a couple of the ladies. You got that, so you explained that carbon is going to take the oxygen, or carbon is going to displace the nickel. The explain bit was the bit that I circled quite a lot on people's papers, and the explanation for it is that carbon is more reactive than the nickel. Okay. Question 2.5. First thing to notice here, we're looking for an answer to 3 significant figures, and if you didn't do it to 3 significant figures, then the most you're going to score is 2 marks. The other thing to notice here is that whenever you see that you're given stuff like this, where you get the atomic numbers and the mass numbers, you can start adding them together to get something. And if we look at where the marks on the mark scheme, first thing is for getting the total MR of the reactants, and that was by adding the nickel oxide and carbon together. There's nickel oxide 75, carbon 12, add them together and we get 87. Great, so then we started off with 87 in total, and the thing we made at the end, just nickel at the end, that's what we wanted, carbon monoxide was a waste product, was 59. So if you look at the calculation here, we got 59 out of the 87 that we put in, so it's decent scores. If you got that on your test for your GCSE in chemistry, you'd probably be quite happy. Well, most of you. So percentage, times it by 100, you're going to end up with 67.8%. Okay. If you messed up on adding up and got numbers wrong in this sort of bit, then you double check, because you can still get, if you did a percentage, you can still get a right mark for calculating the percentage, even if you had the wrong number from, I don't know, just adding it up and getting 58 or something silly instead. Okay. Question 3, powering through. Again, quite well answered. Let's remind you why you'll know what the answer is for this one. You can't use copper and copper or zinc and zinc, because when we did this and we got some lemons and you stabbed metals into it, most people went straight for magnesium, oh it's so reactive, and then stabbed it straight into it, magnesium, and you got no volts coming out of it, because there's no difference in reactivity. Same with copper and zinc and zinc. So the first 2 don't work, it's going to be down to the last 2. Can't be water, because pure water doesn't conduct electricity. Sodium chloride does, and you know that because when we did about ionic bonding, you saw that these white powders, some of them conducted electricity when you dissolved them in water, but they didn't when they were a solid. The other time you've seen it is when we did electrolysis. Sodium chloride is a specific one, seawater, salty water, that you need to know as an example for electrolysis. It does conduct, it's an ionic substance. 3.2 then. Alkaline batteries, why did they stop working? It's a new bit for the new specification. Doesn't mean too much to you though, but it's a chemical reaction. Why does it stop working? A reactant is used up. Some people, cheeky, said that products were used up. That's just the wrong thing to say. Just think about the keywords that you're using. Some people said it. They didn't say that what it is that. So you have to say that the reactants are used up or a specific chemical is used up. You just said it's a bit vague. So try and just think about what it is that you want to say and don't assume that your marker knows what you're trying to say. For 3.3, why can alkaline batteries not be recharged? The reaction is not reversible. Now I know some people got 3.2 and 3.3 mixed up in what they wrote down in the exam and you'll be kicking yourself a little bit there, but always rest assured that you can always learn from that. It is about reading the question and making sure that you answer carefully, having read what you're expecting them to do. Okay. On 3.4, really well answered overall. Most common mistake is when you look at water and seeing that it's got an oxygen in it, people just wrote O rather than writing O2. Oxygen is diatomic. The phone company's named after it. It's one of the things like oxygen, carbon dioxide. Like you just need to know those formulas. Like they're not going to get given to you. Okay. Because it is O2. It means that we're going to need 2 waters, which means we're going to need 2 hydrogens as well. So there's the fully balanced equation on the right hand side. If you only just got the O2 and didn't balance it right, you can still get one of the marks. And we're on the third question, and here is your second 6-mark question. You're probably telling yourself, wow, how many are going to be on this paper? But get them out of the way earlier on. It's easier. In our class, people scored well on it, and people scored well on it nationally too, because you give them the table. And it says use the table and your own knowledge. So even if you just use the table and didn't know anything else, you can still get 4 out of the 6 marks, which is, that's not to be sniffed at. That's good. So when you're talking about this, if you just made some points and they weren't logically linked, then you're getting into the first 2 marks. A lot of people got above that. A lot of people got into 3 or 4 marks, and they got into there because you looked at the table and you said things like the hydrogen fuel cell recharges faster and can travel further. Now, why weren't you getting into 6 marks even if you wrote much more than that? So there's 2 reasons. It might be because you weren't referring to your own knowledge, because the question does specifically demand that. And then the other reason could be because the command word is evaluate. So some people gave me a whole amount of information. I particularly like one person who said about about batteries in cars being stored quite low down, so the car doesn't flip over as easily. Someone who's obviously looked at something like a Tesla before, been interested in it, seen what's going on for it, showing a bit of knowledge. Fantastic. Problem that you do get though is you've not said at the end of it which is best. So if you said the hydrogen fuel cell is best because it recharges faster and can go a longer distance, then you put that judgment in there. You've evaluated it. You looked at the good points, you've looked at the bad points, and you've decided that you liked it better because of these reasons. Okay. Tables on the right have got some of the information that you can get from the table, and some of the information you might have brought in from your own knowledge. Other options could have existed. If you had some from each column, and you made a judgment, that's where you get 6 marks. Question 4. The whole of this question, right, is about the development of the structure of the atom and the theory behind it. So, it starts off with John Dalton and his idea of these indivisible balls, like billiard balls he was playing around with. Like you draw in Year 7, Key Stage 3, draw me a solid, liquids and gas. Think about a solid, those little circles that we're drawing, that's where we're starting off. It's 200 years out of date now though. The next thing that came along was J.J. Thomson, who discovered electrons. So to fit this in, he took the model, and it's Model B, the plum pudding model, and he put the electrons distributed around, and the whole rest of the ball sphere was going to be positive. I can understand if you put E, because it's dead similar, it's just got the charges the other way around. 4.2. Lots of people got it mixed up with 4.3. So 4.2 is the next step. After the gold foil experiment where people were shooting alpha particles, we realised that there was this dense nucleus in the middle and that most of the rest was empty space with electrons flying around it. I didn't know anything about what was inside the nucleus particularly, or you just got these electrons whizzing around, sort of like the clip in the Big Bang Theory in between the scenes. What happened next to get to 4.3? From Bohr's work, Bohr didn't do any extra investigations himself, but what he did was he did some science calculations, he just did some maths, and from the maths he realised that the electrons had to go into particular energy levels. So he brought the idea of these orbitals in here over in option A. So the order we should go is B, and then C, and then A. Okay, now that's not the last bit you need to know about the development of the atom. Put a pin in it, we'll come back to it in a second. Going away to question 4.4. Define the mass number. Well answered overall. It's the protons and the neutrons added together. Most people got that. Dead happy with it. For 4.5, the question's being quite nice and asking you to work out the exact number. People did show me that they could do that just to check what the answer should be. There's two isotopes, a 69 and a 71. If there was 50% of each, you'd expect it to be bang in the middle on 70. It's not. There's more of the 69, so it's closer to 69 than 70, so you'd want to take the second box down to get the mark. And finally, question 4.6, let's take that pin back out again, because we just left where Bohr had added energy levels. In the next step is this guy called Chadwick comes along. Chadwick splits up the nucleus into the protons with the positive bit because he discovers the neutrons with the neutral bit. First mark, Chadwick discovered neutrons. A lot of people didn't get that one, and it's not just in the class, that's from the National Mark Scheme feedback as well. The other thing is, keyword here again, and it's a keyword that I've isolated, highlighted, and told people this is one of the ones that you need to know. It's 2 marks, and it's pretty much this. Isotopes are where they have the same number of protons and different number of neutrons. That'll get you the 2 marks. You can also say they have the same atomic number and a different mass number. And if you look over here, that's pretty much what it's saying here. So to link it into the story, Chadwick's work led to a better understanding of isotopes because isotopes have a different number of neutrons, and that's what he discovered, neutrons. Okay, neutrons are not, or isotopes are not special different forms of compounds. They don't react differently, they react in the same way. In fact, it's just the mass that separates them. Question 5. Right, people just do bar charts right. As long as you remember to label it and do a sensible axis, the scale was easy to plot. You got 2 marks on it. It was nice, bag those, move on. Question 5.2. The student concluded that it's endothermic. It says it's not correct. So thankfully I didn't have anyone disagreeing and saying it was correct. So the reason it wasn't correct is quite rightly, as a lot of people said, the temperature increased. Okay, because exothermic would make things get hotter. For 5.3, temperature change depends on the reactivity. Give a method to describe an unknown metal, how to put it in its place. When they designed the question, they intended you to look at what was already in the question, take that and build on it a little bit. So they expected you to do something like take your unknown metal, place it into a fixed volume of the sulfate solution, and when we're talking about fixed volume, this is one of our control variables. So you could say take 1 gram of each metal, put it into 25 milliliters of a known concentration of each of the sulfates. Just make sure you're doing a fair test each time. Anyway, take your unknown metal, place it into the copper sulfate, and then measure the energy change with a thermometer. So then you can compare it to the other energy changes from the other metals and then compare it. So if it's higher than any of the other metals, it's more reactive. If it's lower than any of the other metals, it's less reactive, and then you can use the numbers to place it somewhere in between. Other things that you could have done, as well as doing that one and giving a control variable like one of these, that's where most people didn't get one of the marks out of the 4. Other things that you could have done was to heat the metal with oxides of other metals and see if there's going to be a temperature change linked to things like a displacement reaction. Or you could have put it in acid and all the other metals in acid and measure the temperature change there. Or you could have set up an electrochemical cell, and obviously the bigger the difference in reactivity, the bigger the voltage. So obviously you intended the first option, but students across the country did come up with those because they're all sort of things that you have done in other parts of the subject, and people did actually use those in their answers, which is cool. So what we're looking for on 5.4 is this. We're looking for a diagram which has got a horizontal line for the reactants. You don't have to label the reactants, but that's what they are. And a horizontal line for the products, and the products are lower. That's because it's exothermic. Some people got really sloppy on labelling the energy changes, and I was quite mean about this. So the activation energy is from that line of the reactants going up and reaching the peak. So it is not just a line which is somewhere in between, it's actually from that point to that point. It's supposed to be quite accurate. And then the energy change is the difference between the reactants at the start and the products at the end. And again, the lines need to be quite clear. So you're getting a mark for getting the correct shape, going from the higher level of energy to the lower energy level, a mark for labelling the activation energy shooting up, and a mark for labelling the energy change, the difference between the reactants and the products. Question done. We're on to question 6. I thought this would be an easier one to do, but actually I think people found this quite difficult. So the key thing that you're looking at here, it says it's solid zinc chloride in the picture. So first thing that we've got an issue with, solid zinc chloride does not conduct electricity. And then it says explain. That's the second mark people were missing. Why? Well, it's an ionic compound. As a solid, it doesn't conduct. As a liquid, it would conduct. Or as a solution, it would, because the ions can move. Okay, so you need to be talking about ions. And like, this is something we've come across in class. People are talking about atoms, particles, electrons, anything else like that. It's that ions are able to move in the liquid, but they're not able to move in a solid. And we've done that in like 6-mark questions and all sorts of, exciting stuff in lesson. For 6.2, this one wasn't answered well, and it's another one of those ones that you just hated at the time when we did it, the structure and bonding ones. So it's graphite. This is one of the ones that you need to know about. Diamond and graphite, covalent bonding. So if you started talking about ions and ionic bonding, you just went down the wrong path. The first mark is the one that most people missed, okay? Graphite is pretty special because unlike things like diamond, where each of the 4 lone electrons gets a pair and they may form 4 covalent bonds, which makes it really, really strong and hard, graphite only forms 3 bonds, which means it's got 1 unpaired electron, which is the second mark. Look at that, 3 bonds, 1 spare electron, 1 delocalized electron, 1 free electron is also allowed. For the third mark, you need to say that those electrons can carry a charge throughout the graphite structure. They can move along the sheet of graphite that's there. Anyway, even if it's talking about conducting electricity, as an absolute stab in the dark, feel free to talk about free electrons carrying a charge or ions carrying a charge. Ions would be wrong in this case, but it's 50-50 as to getting a mark. 6.3. Wow, people did bad at this because they did exactly what I've got on my screen at the moment. They just looked at the question, they wrote the answer, and you ignored that bit at the top. It says the student investigated how the volume of gases produced changes with the time. There is nothing in that can measure a volume. Stop clock's fine. Everything's touching in the right location. There's no gaps between electrodes or something that there shouldn't be. There's nothing to measure a volume. So some people spotted that, but they didn't say what they'd need to do about it. So if you'd use measuring cylinders instead of test tubes, that would have been fine. You could have also said use a burette or any other thing that would measure it. A gas syringe could possibly work as well. And then the explanation why, because the test tube can't measure the volume, or the test tube has no graduations or scales along the side. 6.4, mixed bag. Okay, a lot of people said that hydrogen was proportional, or that it was a straight line graph. Fine, that's good. No one worked out the rate that it was collected at, but it is something that you could do for a mark. Chlorine's where people hemorrhaged marks. Okay, so one quick point: it's not proportional because hydrogen's proportional. It goes through 0. You can see that. The chlorine, it's curving at the end, so that's not proportional. It's still a straight line graph. It's still after 8 minutes that as the time increases, the volume of the gas increases, which you could have said as well. Look at that, after 8 minutes, the rate of collection of chlorine is the same as that of hydrogen. But the first bit, the rate changes. So initially, up until 8 minutes, the rate of collection of of chlorine is changing. So there's 2 statements to say. So looking at the graph, there's one thing to talk about, there's a second thing to talk about, and there's a third thing to talk about for 3 marks. 6.5. It tells you in the question here, the number of moles or the amount of each gas is the same. So you can't say there's a different amount. It says non-escapes. So where is it going to? Look at the apparatus. Where could the gas go? Where do you find chlorine? Swimming pools. What's it doing in a swimming pool? Oh, it's dissolved in it. Only maybe like one person possibly got this. The volume of chlorine is less because the chlorine is dissolved in the water. Clever person. 6.6. Calculate the moles of chlorine collected after 20 minutes. It says use figure 8. So let's just go take that first line and go back to figure 8. 20 minutes. 20 minutes. What can I do from there? Talking about chlorine, so let's go up. There's chlorine. And then we go across. Now we are 1, 2, 3 little diddly boppers up, and we're going to go across, which should bring us out at around about 6.6. Because that would be 6.8, and then that would be 7 slap bang in the middle between the 2. So, first thing, we just wrote down that 6.6 centimetres cubed of gas. You can get your first mark. Well done. you read the question. The next thing to look, the volume of 1 mole of any gas at room temperature is 24 decimeters cubed. Some people decided to argue with that. It doesn't matter what gas it is. If you had 1 mole of it, it takes up 24 litres or 24 decimeters cubed. That's a fact. That's a constant. Okay? You've got 6.6 centimetres cubed, and you want to know how much that is out of 24 decimeters cubed. The problem there is that you've got to convert the units, centimetres cubed and decimeters cubed. So we get our 6.6 and we divide that by 1,000, and that gives us 0.0066 decimeters cubed. And I can't remember anyone doing that to get full marks on this. So that's where your extra mark would have come from. But then, if you find out how many 0.0066 decimeters cubed fit into the 24, you can find out how many fractions of a mole that you've got. So in this case, if you've got that in the calculator, 2.75 times 10 to the minus 4, because it says give your answer in standard form. So a quick reminder, standard form is where you have a number between 1 and 9. If it goes up to 10, then you move it along another decimal place, and then you put in the times 10 for, and however many decimal places you move it. So times 10 to the 4 would be adding 4, moving the decimal place 4 times to the right, and minus 4 means 4 times to the left, meaning this is going to be a smaller number, a decimal number. Okay. Obviously on the right hand side it does tell you that you're allowed to make mistakes in the early bit, and then if you carry those mistakes through and do the right sort of calculation, so if you've got a duff answer for the volume, but because you did hydrogen instead of chlorine, for example, but then you were able to then divide that by 24 and get an answer here, then you can still get some of the marks. Okay. Right, speeding on to question 7, because we love chemistry and we want to keep going. Products formed. Oh, clue. Products. Plural. So if people got this wrong quite often, it's because they named just one product and it was probably potassium chloride, because like, I remember this is a bit of chemistry they get. Channing Tatum just walked into the club and saw Kim and Kanye, and now I've got a Channing Kim, but you forgot to mention where Kanye was. He's still at the bar crying. If you don't know what that means, it's basically that chlorine came in, it pushed iodine out, and it ended up with potassium as potassium chloride, but then iodine still exists, it's just been pushed out on its own. So both of these we needed for the mark. The 7.2. Why is chlorine more reactive than iodine? I was impressed at people for this one, because people remembered this, and it is some pretty tough stuff, so it must just be because you've got an amazing teacher. It couldn't be any other reason, like you work hard or your books are fantastic or anything silly like that. So, people that are getting this right were saying that chlorine's outer electrons are closer to the nucleus. Because they're closer to the nucleus, it means that it's easier to add the extra electron. Some of you said lose, wrong way around. Add the extra electron, and it needs to go from 7 in its outer shell to 8. It's easier because there is a stronger force of attraction. So there's 3 real points we want to say. Electrons are closer to the nucleus, stronger force of attraction, and that means it's easier to gain an electron. Okay. Notice it does say over here that you can only get 2 marks out of 3 if you keep talking about chlorine rather than chloride. That is a common mistake. People getting the ides and the enes mixed up. Ides are in the compounds, enes are as the element on their own. Okay, it is a different thing, so I'm not just being pedantic. 7.3. Chlorine reacts with hydrogen to form hydrogen chloride. Why is hydrogen chloride a gas at room temperature? Answer in terms of structure and bonding. So it's going to be a question you hate straight away because you didn't like structure and bonding. So, first thing is hydrogen and chlorine is going to be HCl. We've seen that before. That's what hydrochloric acid is, isn't it? It's not a repeating pattern. It's not a giant structure. It is simple molecular or simple covalent. Just by saying that, simple covalent or simple molecular, and identifying the type of bonding, 1 mark out of 3 bagged. That's probably the 1 mark that people didn't get if they were doing well on this. I was impressed that people did remember what I said, that they have weak intermolecular forces. I allowed you to say intermolecular bonds, but if you just said weak bonds, you're lying, because the bond between the hydrogen and chlorine is incredibly strong. It's a covalent bond. It's really strong, the same ones you find in diamond. The intermolecular, or the bonds between molecules, better to say the intermolecular forces, they're weak. And because they're weak, that's the second mark, it takes little energy to overcome them. That's the 3rd mark. Okay? Well, maybe not okay, but hopefully we'll get that point, because that's pretty important. It's one of the things I do annoy people with going over and over when we're doing the lessons. Wow, 7.4. Again, mega impressed. A lot of people got marks on this. Super impressed with what you did on it. So what I like is that you did the key thing that you should do. You added all the stuff up on the left, the carbon and hydrogens here and the bromines there, and you got one figure, and then you added them all up on the right, the carbons and hydrogens and the carbon bromines and hydrogen bromines on the right, and you got these some totals. So on the left hand side, you added them up together, should have got 1841, there's a mark. On the right hand side, you should have got that there's 1602 plus X, and X is the unknown bond between the C and the Br, so you know you're missing that. The other key bit in the table that you really need to look at, the overall energy change is minus 51. So when you're doing your overall calculation and finding the difference between the two numbers, some people didn't take that number into account, so your number was off. Okay, that's why you were out by a small amount. So if you know that minus 51 is equal to 1841 minus everything on the right, the 1602 and the X, then you can resolve that, you can simplify it down, and you'll work out that it's 290. And a lot of people got that it's 290. So people that got 188 to go at 3 marks, generally what you didn't know is that when you minus a minus, it's a plus. That's a math thing. So if you're taking away minus 51, then you're actually adding 51. So you just went the wrong way. Otherwise, you're doing the right sort of thing, and you did really well. So I was really impressed. Question 8. Nearly there now. One hazard associated with stage 1. What the exam board are expecting you to do is notice that there's chlorine in there, which is, a chemical weapon. It's pretty dangerous. It's toxic. And when we're talking about the dangers, we want to know exactly what the problem is. Don't just say chlorine's bad, okay? It's chlorine is toxic. It's not harmful. Harmful makes your skin go a bit itchy and stuff like that. It's poisonous or toxic. What a lot of people went for, though, they spotted this carbon monoxide. It's not carbon dioxide, the people that said that, naughty. It's carbon monoxide, which is also poisonous. So we could have that, and they allowed titanium chloride is corrosive if you knew that, but no one did, so not a problem. 8.2. So I'm going to keep that up there just so I can see stage 2, because we're talking about this one now. And it says, why must water be kept away from it? What would happen if it came into contact with sodium? Some people put it fizzes. This is an industrial process, ladies and gents. This is not like Mr. Dawson cutting off a tiny little pea-sized amount and dropping it in the water. This is the equivalent where you say, let's get the whole tub of it. In fact, instead of just getting the whole tub of it, let's get an absolute bucket load of it and throw it in. What's it going to do? Is it a fizz? Is that a problem? No, it's hazardous. Why would it be really dangerous? So if you just said it is a very vigorous reaction, or it's very exothermic, or it produces a very corrosive hydroxide solution, that's all right. If you said it's explosive, we can have that too. Because this is a large chunk of it, it'll make a lot of hydrogen, it'll possibly explode, it'll definitely get hot enough to set on fire. It's not cool. 8.3. Suggest why it's carried out in an atmosphere of oxygen and in air. I'll think about what we just said. If oxygen was around, it might oxidise it, so it might react with it. Or other things that are in air might react with it, like water. And we just said what water in their sodium is going to be like. That's the mark that a lot of people got, and you ignored the argon bit. So boost your mark, talk about argon. Argon is a noble gas, is unreactive or inert, so it would not react with it. So if you put argon there, it means that oxygen or water isn't there. That's the bit that you need to add in. 8.4 then. Titanium chloride. Let's just look at that. Titanium, metal, chlorine, non-metal. Metal and a non-metal. Which sort of bonding is it? Oh god, I hate bonding. Well, that's what you're saying anyway, probably. It's ionic, okay? So, explain why you'd expect titanium chloride to be not to be a liquid at room temperature. Let's just suppose it is ionic. Have a mark for saying it's ionic. Well, if it's ionic, it means that ionic substances are generally solids at room temperature. Or you could say the why that is, which is they've got high melting and boiling points, and that's your second mark. And then the third bit is explaining why you've got that. So it's because they've got really strong electrostatic forces, or the ionic bond has got very strong forces of attraction between them, so you need a lot of energy to overcome it. Now, you could have got 2 marks going the other way around. If you said that titanium chloride must be simple covalent because it's only got small molecules, although they've got strong bonds between the actual atoms, the intermolecular forces could be weak, which means that then they'd be quite easy to separate, in which case they turn into a gas. But either way, it's not a liquid. So you could have said it either way around. For 5.5, did good on this. It says sodium atoms are oxidised to sodium ions. Why is this an oxidation reaction? Not only did you say that they're losing electrons, because oil rig oxidation is loss of electrons. A lot of people said sodium loses electrons, which is really specific because it's what the examiner wants. You don't say it, you say sodium. Some people just said oxidation, it's adding oxygen, but it says it's a displacement from titanium to titanium chloride. There isn't any oxygen there, so you can't talk about it in terms of oxygen in this case, unfortunately, which makes this one of the higher level questions that I talked about. And again, half equations, a lot of you panicked over these, but look how easy this one could be for you. Sodium, now someone's got to explain to me why people keep thinking that there's going to be 2 electrons in this, and 2 sodiums, or an Na2+, because I need to work out why you've got that misconception. Sodium's in group 1, it's got 1 electron in its outer shell, it's going to form a 1+, which means it's going to lose 1 electron. So it's literally going to be Na+ and E-, and it's got 2 gaps in there. And you know which half equations have got some E- in there, so we can have a guess at least. A lot of you had really good guesses. 8.7 then, moles. Right, so what this one wanted you to do was show you working out. So anyone that just wrote a paragraph, you weren't getting the marks for this one. But then some really clever people just did calculations and didn't do the explaining. So let's put the two together. Again, you see these numbers up here? We start adding them together. And it's asking about titanium chloride. So let's do the sensible thing. Let's work out what the mass of the titanium and chlorine in titanium chloride would be, which is TiCl4. Add them all together. There's your first mark. We've got 190. So where I could see that in there, where you've clearly attributed that to the molecular mass of the molecule, I gave you the mark, even if all you did was just work out what the molecular mass of every single thing in the equation is. You got 1 of the 4, and you did good, so bag that mark and be happy about it. So, the number of moles of it, if we're doing this technically, right, it's 20 kilograms of sodium, so that means it's 20,000 grams. So the mass equals Mr. Moles, rearrange it, the number of moles is 20,000 divided by 23, so there's 870 moles. But we do allow the fact that if you just said 20, because it's at the same ratio, you could have 0.87 moles if there was 20 grams instead of 20 kilograms. Same way around, if we're looking at how many moles of titanium chloride there is, it would be 40,000. But again, if you just did 40 divided by 190, then you'd get 0.211. So, how do we know that titanium chloride is the limiting reactant? Well, if you look at them, there are a lot less moles required than what's in there. So you've got 211 moles of titanium chloride, and that's less than the 217.5 moles needed, or 870 moles of sodium is needed, more than the 844. So whichever way around you look at it, you've not got enough titanium chloride, or you'd have too much sodium. When you look at how many actual moles there are. What you can't just do is say that it must be sodium because there's less sodium than there is of titanium chloride, because the mass in kilograms doesn't mean that there's more of it. It comes back to the lesson where we were talking about pairs of socks and moles and things like that. It wasn't a favourite one for you, I've got to be honest, but some people got a good number of marks there. I was really impressed. 8.8. So we're being told that the most you could make here is 13.5. So if you did that perfectly and you did this reaction perfectly, which doesn't happen, at the end you'd end up with 13.5 kilograms. You'd have 13.5 out of 13.5. That's 100% on anyone's test. Okay? You didn't get that, because you don't get that. So what you did get was 92.3% of it. So we need to find out what 92.3% of 13.5 is. Loads of different ways you can do that. Get the mark scheme for one of them. But if you know that 13.5 is 100, that means that 1.35 is 10%, or 0.135 is what 1% is, times that by 92.3, and you end up with what 92.3% is. It should be 12.5. A lot of people left it to 12.46. Why have we kept it to 12.5? Well, if you look, 92.3 and 13.5, they're each 3 significant figures, so you just generally follow the convention of what's in the question. You're not accurate to 5 levels, 5 decimal places. Getting on there, question 9, here we go, not long to go now, so thanks for staying with me. Acids and alkalis. Why can an acid be described as both strong and dilute? Right, so if I look back at why people were getting things wrong on this one, people describe what diluted means. They didn't say what dilute means. So diluted, they said, is where you add water to something. But where it is dilute is because there is a small amount of the acid because there's a larger amount of the water. And you have to say what it means if it's dilute. Okay, so I could, if we're talking about like cordial, for example, dilute is how you drink it. You don't drink it concentrated out of the bottle unless you're weird. But it's not like just adding a little bit of water. If I put like a thimble full of water in it and diluted it a bit, it's not dilute then, is it? It's got to have a lot more water in it. So most people needed that mark. Some people, but only some people, got what it meant by a strong acid. So strong acid is about whether it fully dissociates or not. So strong acids fully dissociate in solution, weak acids do not. And that's the key thing that we're looking for there. For the next one, we need to know that the pH is a base 10 system. So when you go from pH 3 to pH 4, you'd have 10 times less hydrogen ions. So here, handily, we're starting off with a concentration of 1 times 10 to the minus 3, and we're going to 1 times 10 to the minus 5. So that's not just 10 times less, that is 100 times less hydrogen ions. So it's basically going to change the pH by 2. So we're going to go from pH 3 to pH 5. Some people went the wrong way, and they went to pH 1 because you went through the opposite direction. It's just a case of asking yourself, if we're diluting it, if we're making it weaker, would that actually make the pH lower or higher? And then just common sense it for me. For people that like to guess, it's going to be a number between 1 and 14, isn't it? It's pH. Looks like it's going to be a nice sensible number too. Right, 9.3. People always panic about titrations, but there's 5 marks on this. And you know what? You can even get a couple of these without too much effort. So the first thing it tells you, which is really, really useful, is it says, use only the student's concordant results. It's not even hiding this from you, it's telling you. And if you don't even know what concordant is, it's even telling you that. Those that are within 0.1 of each other. So the 3 that are within each other are these 3. So if you use those 3 answers or highlighted them as the ones to use or labelled the 2 as anomalies, there's your first mark out of 5, and you didn't even have to understand what a titration was. You read the question and you had a go and you got 1 of the marks. So well done. Second thing was that you'd make an average out of it, which is not something you needed me to teach you. You add those 3 up, you divide it by 3, and then you get an average titer of 22.13. 200, shut up. 22.13. So first 2 marks we've got are choosing titrations 3, 4 and 5 and working out what the average out of the 3 is. So the next bit is the calculation, and I understand this is where we lose a few people, but it's not a problem. You can do the C1 V1 equals C2 V2 that I've taught you in class. I don't think I saw many people doing that, but then I didn't see many people getting this correct. Or, because you now know the average titration of the hydroxide solution, and you know the number of, its concentration, you can work out its number of moles. You notice here that I've divided it by 1,000. I say I have, the mark scheme has, because it's turning it into decimeters cubed. So we get our volume, times it by our concentration, that'll give us our number of moles. Here's the bit where even the best people missed it out. Now, the number of moles of sulfuric acid, it looks like it's less than that. In fact, it's half of it. Why is it half? Let's look at the equation. We know that there is 0.002324 of this stuff, and we want to know how much of this stuff there is. That's got a 2 in front of it. This one hasn't, so it must be half of it. Cheeky. That is a nasty one, but this is the last question at the end, and it is intentionally mean to try and distinguish between those getting 8s and 9s. Then we can put that number into concentration. So the concentration is the number of moles divided by the volume. It's times by 1,000 there because we want to turn it into the decimeters cubed. So that gives us 0.0465 moles per decimeter cubed. Okay. There are some examples here on the right hand side where you can score some of the marks because you did some of the steps correctly, and again, if you messed up the step 1 and you added them all up and used the average from that, if you continue that average all the way through, you can still get marks for the rest of the steps that are described, even if you didn't get them for doing the average. Okay, errors aren't in the first bit of the question aren't carried forward and penalising you on and on forever and ever. Okay. 9.4. Not well answered. So the pipette is used to measure a fixed amount really, really accurately, whereas the burette is used to measure the volume bit by bit. So it's a variable volume. So it could be 23, it could be 23.5. So just make sure when you're talking about these, you're really specific. Look at the way the question's broken down. Why do you need a burette for one and sodium hydroxide for the other? Because commonly people are saying so they don't react with each other, and I get why you're saying that. But then why would you have two different pieces of kit? And then you should think back to how the titration actually goes, how you carry it out, and then get that little clue. Right, so the last one. 9.5. So on 9.5, the way I'd expect you to get the answer is first of all work out the number of moles that you've got present. So you've got 30 centimetres cubed of a 0.105 mole per decimetre cubed solutions. The problem there is they're not in the same units. So when you look at the example calculation over here, that's why we've converted by dividing by 1,000 to get 30 centimetres cubed into decimetres cubed. So the reason it's times it by 0.105 is to work out the concentration. It's the number of moles divided by the volume. So if you want to work out what the number of moles is, you're going to have to get the concentration and times that by the number of moles. So you should come out with 0.00315 moles. And obviously, if you didn't divide that by 1,000, first of all, it's going to be 3.15. You'd then say, right, so if 1 mole weighs 40, how would I find out what 0.00315 weighs? So that is mass equals Mr. Moles. Mass is going to be the MR, that's 40, times by the answer from before, so that'd be 0.00315, or that's the sum that we did before there, times by 40, it'll give you a 0.0126 grams. If you did 126 grams as an answer at the end, you did all that sort of stuff. You just forgot to change the volume, which is kind of annoying, because that was actually quite a tricky question, but well done for getting one of the marks out of 2 anyway. The other way that you could get it is you could work out that in that solution there'd be 4.2 grams dissolved, which would be working how much there is. You just got to scale it for the 30 centimetres that you've actually got, so you'd come out with 0.126, because that'd be 4.2 grams in the litre. So in half a litre you'd have 2.1, and you keep going down all the way until you get to 0.126 for the 0.00315 moles that you've got. Okay, well done on the test, ladies and gents. You've got some really, really fantastic scores on there. You do look at the questions that you got wrong, the ones that you need to look at improvements. Match that with going on things like freesciencelessons.com, looking at that particular area. Ask me if you don't know where it is, what you're doing to look at it, or ask me where it is in the revision guide, so you can find that area, you can target it, and you can do that revision and make it better. There's nothing really that you can be doing that's better than looking at past papers, analysing the way that the questions are asked, what the examiner wants, looking at the mark scheme, looking at what you wrote, and then evaluating your performance and getting better. Okay, so really can't stress it enough. That is what you need to be doing from now on. Thanks very much.